Okay, let's get started. Once we all get in. So I am Eric Demain, new professor here. This is my first week at MIT, so it's quite an experience. Professor Charles Leiserson and I will be both teaching the lectures, roughly half and half, maybe alternating every week or so. And it's really exciting to be here because one of my favorite things in the world is algorithms. And in fact, all three of us, one of our favorite things in the world are algorithms. Algorithms are fun, and that's what we'll try to convince you of in class. Now, having said that, today will not be the most exciting lecture, I'm afraid, because we won't actually talk about algorithms explicitly. But we need to set the stage a little. So today we're going to talk about solving recurrences. Which will be very important for determining how fast our algorithms are running. And in particular, on Wednesday's lecture, we'll see lots of examples of where recurrences arise with algorithms. First, I should make a couple of announcements. So in the first class, there was a quiz 0 assigned. If you weren't there, you've got to fill out quiz 0. And furthermore, come up after class so that we can get you assigned to a recitation if you don't have one already. Problem set 1, in your calendar it says it's due next Friday, I think. But you can have till this Wednesday, a week Wednesday. Okay, so that's good. Lots of time. Goes over the long weekend. Okay, those are announcements. So why do we want to solve recurrences? Well, we saw last class with merge sort, we got this very simple recurrence. T of n, something like this. Okay, and we need to solve T of n. And you've all seen how to solve recurrences, presumably in like 604.2 for the MIT students. I'm trying to memorize all these numbers, but bear with me. Okay, we need to solve them to know how fast our algorithms are going. And some of today's lecture will be review from things you've seen before, but it'll go into more depth. And in particular, we'll see the connections to algorithms. Although we won't be talking explicitly about algorithms, there'll be algorithms lurking behind all of this to make it more interesting. Okay, the first, so in total, I think there'll be 3 different methods I'll be presenting today. The first one is called the substitution method. How many people have seen the substitution method before? 25. Good. So maybe a quarter of the class or so. The substitution method is very general. It's the most general method because it applies to every recurrence, which is great. You can use the substitution method to solve anything. There's a slight catch, which is that you already have to know the answer. Okay. So to apply the substitution method, you don't have to know exactly what the answer is, but you need to know some guess of the general form of the solution. And then the idea will be that you apply induction and check whether this guess works out. So you verify the guess. By induction. And when you do that, you'll actually figure out not just the form of the solution, but you'll get the constants as well. Good. So let's look at an example, make it clear what's going on here. So I'll change, not exactly merge sort. This is a recurrence, but you can think of it as an algorithm. It says if you have a problem of size n, you split that up into 4 problems of size n over 2. And then you solve those recursively. And then you merge them with a linear cost. Okay, so it's an algorithm or a recurrence. And now you want to solve it. And let's not think very hard. Let's just make a random guess that for now, let's say t of n is at most n cubed. And that will turn out to be true. So let's try to prove it. We'll prove it by induction. So the induction hypothesis is, we'll assume that t of k, let's say, is at most some constant times k cubed for all k strictly less than n. And then our goal is to prove it for n. Okay, standard setup. I'll write it explicitly here, but then not again. Okay, so this is induction. Good. You all remember. It's seeping back into your minds from last semester over the summer. Okay, now comes the substitution method. Now, substitution means we're going to plug something in. We will take this recurrence and plug in the induction hypothesis to the recurrence. So we have t of n, and we know that it's 4 times t of n over 2 plus n. And n over 2 is strictly less than n, and so we can apply induction. So this is the substitution method. We just say, well, that's at most 4 times c n over 2 cubed plus n. One thing I want to stress here is that the induction hypothesis was not that t of k is order k cubed. That won't be strong enough for our purposes. We really need to expand out the big O notation into a constant. The reason for that, maybe I should ask you, why do we do that? Why do we bother throwing away our wonderful big O notation and going directly to constants? A little early in the morning. Yeah?
It can result in a stronger induction hypothesis, thereby making things easier.
Right. We get a stronger induction hypothesis. Good. If we said big O of k cubed here, we wouldn't know what the constant is. And so it might be different for different, well, if we can write down c, we can use c, and that will be useful. In general, there's a stronger thing going on, which is that you really cannot use big O notation with induction. Okay, if you could, you can prove things like 1 plus 1 plus 1 n times. Let me write this down. If you have n of those, you can prove that that's order 1 by induction, except that it's wrong. Right? You shouldn't be able to prove that. Say, well, 1 is order 1, and then you add another 1. Each time it's still constant. But the constant is changing. And so this is really cheating. And that would happen here. If we use big O's, we'd be proving things that just aren't true. So we don't want to do it. So that's why I'm using C. The underlying reason is that big O just isn't a very powerful notation. You can manipulate it in certain ways that you can prove by theorems, but not all the time, and especially not with induction. Let's rub it in. OK. Where are we? We have this. We should expand it out, maybe. What is, so it's something times n cubed plus n. Lead constant is 1/2, yeah. C over 2. Thank you. Right. 8 on the bottom. OK, now what's our induction hypothesis? We want to prove that that's at most c times n cubed. And the first thing you should check is that this looks like it's going to work out intuitively, right? The most important term here is the n cubed. There's a lower order term, but that's not going to hurt us so much. We have an n cubed in front with a c over 2 in front, and we want to show that that's at most c times n cubed. So that's looking good, because the lead constant is smaller. We should be able to absorb the lower order term into here. So that's the intuition. Now to make that formal, we want to, a much easier way to do this is to write it as c times n cubed. Write what we have as c times n cubed minus some term. So the form here is we're writing what we want, this desired c times n cubed minus the residual. Okay. So what is the residual here? If we want to make this term equal to this, we should subtract off don't be shy. C over 2 n cubed minus n, right. The two minus signs here cancel, so you get a plus n, and that's what we want. Now this will be at most c times n cubed as long as this residual term is positive, or at least non-negative. So this is true if c over 2 n cubed minus n is at least 0. And when will that be true? So now we get to choose our constant c. We haven't assumed anything about c. So we might as well assume that c is at least 2 over n squared. That would work. We can, we've got lots of freedom here. We can assume that n's sufficiently large. So instead of c at least 2 over n squared, we can just say c is at least 2 and n is at least 1. That'll do. And you check as long as these constants match, and then if n is, n cubed is growing bigger than n, so that'll be good, as long as n's big enough. Okay. So that seems to have done it, right? We've proved that t of n is at most c times n cubed, as long as c is at least 2 and n is at least 1. Am I leaving anything out? Or is this the end of the proof? Well, I'm asking. So what's missing from this proof? Yeah. The base case, right. If I'm doing an induction, I need to have a base case. And I've also sort of cheated you a little because I have here a recurrence, but I didn't specify the initial conditions. So that's why it may have not been so obvious that we need a base case. So we need to base, what's the right word here? We need to ground the induction. That sounds good. With some base cases. And the reason I didn't specify the initial conditions for this recurrence is that they're pretty standard. When you're dealing with algorithms, if your n is small, if n is a constant, well, your algorithm can't do very much. If I give you an input of size 5 or whatever, well, it could spend 5 cubed or 5 factorial operations. It's all constant. So we can assume that t of n is constant for n smaller than some constant n0. And we'll do that pretty much all of the time. So we'll typically omit this explicitly saying the initial conditions. I should mention again that this is a bit of an abusive notation because nothing's going to infinity. This isn't really asymptotics, but it's just convenient notation for saying this is constant. Okay. Those are our initial conditions. Now all we need is a base case. Well, if we have n, let's say n is at least 1, and it's at most this constant n0, then we know that t of n is a constant. And so, in particular, it should be at most c times n cubed, as long as we choose c large enough. So I'll just continue up here. So again, we're free to choose c. So if we choose it large enough, that'll hold. We're just dealing with constants here, so it's really easy to get a base case. Okay, that's the end of the proof. Any questions so far? That was our first example of the substitution method. We'll see another one. Good. So the next natural question is, well, we proved that T of n is big O of n cubed. Is it big theta of n cubed? So is this bound tight? Any ideas? Yeah?
No, it's not.
Right. What is the right answer for T of n?
N log n.
N log n. Close. It's on the right direction, but you've already answered a couple times. So anyone else? Just speak a polynomial. N, is it n? Splitting into 4 subproblems. If this were a 2, you'd be right. It would be n log n, because that's merge sort. But it's 4. You're splitting into more problems. So you think, well, let's see. I have a polynomial. When I double the input to get from n over 2 to n, I multiply the output by 4. So I have x to the k, and when I double x, I quadruple x to the k. What polynomial does that sound like? Squared, right? Okay, so that's just intuition. Okay, we're not proving anything, but it's useful to think that way. So we'll say this bound isn't tight. And so our next guess is that T of n is order n squared. So that's what we'll try to prove next, again using the substitution method. So let's go through all the same motions. I won't write down quite as many of the steps. So we want to write down the induction hypothesis. We assume that T of k is at most some constant times k cubed, provided k is less than n. And then we want to prove that T of n is at most c times n cubed.
Squared.
Thank you. We already did cubed, so we have to go to squared. You all have these announcements, hopefully. Good. So we have T of n. We want to conclude in the end. Not doing a very good job here. T of n is at most c times n squared. Good. How do we proceed? Well, we take, again, the recursion. The recursion tells us that T of n is 4 times T of n over 2 plus n. Now we have a stronger induction hypothesis, which says that that is at most 4 times c n over 2 squared instead of cubed. We want to prove, well, this is at most cn squared. Well, we went through a lot of work last time. Why don't we just say, well, that's order n squared. Right, all we want to do is prove that T of n is order n squared. Okay, and that's the induction step, and then you need a base case. The base case is the same. Okay? So we all understand the substitution method. Go on to the next one.
Question. The induction method doesn't seem to work to evaluate a second line with 4c or cn squared plus n. And that's
Yes.
not correct. So what do we do now?
Yeah, okay, so one thing we can do is expand this out. Let me add in another line. just to see what we're dealing with here. Yeah, when we expand this out, you get just cn squared, because the constants cancel. You think, well, gee, that wasn't at most c times n squared. So what's going on wrong here? Why isn't this enough? Why can't I just end the proof here? Yeah? Yeah, c would have to be different. This is sort of getting back to what I said in the beginning. We can't use big O notation in induction. We have to write out the c's explicitly, because here it's not working out. C times n squared plus n. Well, so let me get rid of this. C times n squared plus n, that's c times n squared. If you want to write it minus a residual, it's minus negative n. And there's no way that minus n is going to be positive. So this is never true. So for no choice of c, can I get this to work out? Seems like a bit of trouble, so right. Sad face. What's going on wrong here? Here we had, the reason it wasn't enough for me to conclude that it's order n squared is that was not my induction hypothesis. My induction hypothesis, way over here, was that t of k was at most c times k squared, not just any constant, but c. Okay, so you cannot use big O. Stick to your constants. Good. I'm driving this in, but if I don't drive it in, people will do this on their problem sets. So I apologize for belaboring. So what should we do? We need a new idea. Right? This proof isn't going to work out. We still think in our heads the t of n ought to be n squared. But we need something better. This induction just didn't cut it. Any ideas on what to do next? I won't cheat and look at my notes. So I need your help. Any ideas? This is induction, right? This is 6042. Want to prove a theorem? We know in our hearts that it's true. No, we have to prove it. Otherwise, we'll just have to go home. That may sound like an attractive option, but no, we have to cover the material. How do we finish this proof off? No ideas. Come on, you TAs have to know. Oh, that's too strong. We want to strengthen the induction hypothesis. Yeah. You want to add a linear term. Good. So we want to strengthen the induction hypothesis. If we strengthen the induction hypothesis, maybe we can prove something stronger. Right? You were saying in the beginning, we were not going to assume just big O here. We'll assume that it's at most C. That's stronger. So it may allow us to prove something stronger. So that's what we want to do. Now the question is how? And one suggestion from Bob is that we take t of n. We say, well, t of n may not be exactly, let's write t of k here. It may not be exactly some c times k cubed. Let's call that c1. But squared, thank you. But maybe, there's an additive term, c2 times k. But that's not actually a stronger assumption. Right? That's actually increasing the upper bound. And so this is rather counterintuitive, but the right thing to do is not add, but subtract. The reason that's a good thing, so we're going to subtract a lower order term. The reason that's a good thing is we want to strengthen the induction hypothesis so we can prove stronger things. If we subtract off something, we have a better start going into this proof. And so hopefully we can prove something stronger. So that's counterintuitive, but it turns out to be the right thing. If you added, then you just discover that C2 is negative. But here we'll discover that C2 is positive. OK, so let's give it a try. This is our new induction hypothesis. And now we start with T of n. We know, again, that it's this. And now we plug in our induction hypothesis into this term. And we get T of n is at most 4 times C1 n over 2 squared minus C2 n over 2. And we should carry over an additive n. OK, so let's expand that out. It's something times n squared. I guess just C1. All right, 4's cancel. Minus C2. Sorry. This is also multiplied by 4. So we have C2 over 2 times n plus n. OK? Did I make a mistake? 2C2. Whew. Good. You know, you've probably all heard this before, but there are 3 kinds of mathematicians: those who can add and those who can't. Bad joke. I'm one of the latter kind, but that's why I have you all to help me out in not making mistakes. I will make mistakes all the time. Please tell me, because otherwise the proofs won't work. If we left that as C2 over 2, and I know because I tried it yesterday, I made the same mistake, the proof would not work. Everything would be negative. Fortunately, if you do correct arithmetic, this will be right. Let's hope. All right. So we're here. We want to prove, let me just rewrite it so we have it at our fingertips, or at my fingertips. We want to prove that that's at most C1 n squared minus C2 n. That was our induction hypothesis. Well, let's write it in this form of desired minus residual. So we'll write it as C1 n squared minus C2 n minus something. And instead of doing it wrong, I will ask you, what's the right answer? C2n minus n, yeah? Right, so I've only subtracted up one C2n, so I need to subtract up another. The 2 minus signs cancel. Good. So when will this be at most this? Well, whenever this residual term, C2n minus n, is non-negative. And when's that true? C2 is at least 1. Let's say, for example, we can choose C2 to be at least 1. Good. And that finishes off the proof. Again, you have to do a base case, but I won't write it down here. And so we've proved that T of n is order n squared. Not only that, it's at most C1 times k squared minus 1 times k. Or I should be saying n when I say k, but everything OK? What about C1? We haven't assumed anything about C1. So is it really at most C1 n squared for any value of C1? It's a little fishy. That makes it sound like it's less than n squared, but you can check it's actually n squared. So what about C1? Do you have a no? I've been a little sly here, but that's what makes you think. So let's go back. We know we're here. Do we assume anything about C1? That's right. Everything I've written here is good. It's what I haven't written. Yeah?
C1 has to be positive for the base case?
For the base case, right. So C1 has to be positive for the base case. Actually, it has to be a little more than positive. Where do we have a base case? Here. So in the base case, as long as n is at most a constant, we knew that T of n was a constant. And we don't know what constant. It could be 163 for n equals 1. OK? We said, well, that's at most c times n cubed, or whatever our bound is. as long as C is sufficiently large. And that's where C1 matters. So C1 is constrained. We have to choose it large enough for the initial conditions to work out. And for the base case to work out. OK, and that ends the proof. Now, what does this tell us about the algorithm? It says, well, if we have our algorithm, we want to implement it, because in the end, algorithms are actually useful. We have this running time. It splits it into 4 subproblems, size n over 2. Then it does this merge cost of n. Well, what we care about in the running time is the lead term. The linear term is minor. We want to make this as small as possible. And the only thing constraining the constant in the lead term is C1. I mean, that is the constant. It's only constrained by the initial condition, by the base case in your algorithm. So what this is saying is if you can optimize the base case in your algorithm, if you can solve problems of size 1 and 2 and 3 faster, the whole algorithm will run a lot faster. So this, we'll come back to this, but this is, we're learning something by solving the recurrence about how fast this program is going. So that's good. That's why we do this math. OK, that's all I want to say about the substitution method. Stop me if there are any questions. Otherwise, we'll go on to recursion trees. One thing I should say is I've only been talking about upper bounds, right? Always big O. Really what you want to prove is big theta. And the easiest way to do that is to split it into 2 parts. You split a big theta into a big O and a big omega. You prove the big O just like I've been doing here. And you prove the big theta in exactly the same way. So if you want something to try at home in your spare time, you can prove that this T of n is also at least order n squared. OK, but let's go on to recursion trees. So let me just say a couple things about recursion trees, then we'll do an example. The idea is to model what's going on in this recursion. So we'll think of the recursion as a recursive algorithm. And then we just watch what happens as that algorithm executes. And why do we want recursion trees? They're another tool. We're going to learn a bunch of tools for solving recursions. Then you use whichever tool you feel fits right with the problem, and then you can solve the recursion. Now, recursion trees, you can use them to solve a recursion explicitly. The easiest thing to do is for generating a guess of what you think the right answer should be. For using your mind and just thinking, intuitively what's going on. So we'll get a guess, and then we'll use that guess for the substitution method. OK, that'll be the idea. So let's just see what's going on. Let's take another example. Say T of n is T of n over 4 plus T of n over 2 plus n squared. I want to make it interesting. OK, so now we just run the algorithm. We see what happens. We start out with a problem of size n. We split that into a problem of size n over 4 and a problem of size n over 2. That's what this notation means. Solve those 2 subproblems recursively, and then you merge them. I'll draw it like this, with a cost of n squared, to remember my exponents. OK? Then you just keep expanding. So if we expand that again, we'll get these merge costs. N over 16 8, either n over 8, n over 4. Okay, and you keep going. Do it once more, sort of. Then at some point you say dot, dot, dot. Dot, dot, dot is the mathematician's friend, except it's not entirely rigorous. But it sure is useful. So now we say, well, keep going. In the end, and now we're using our intelligence, we say, well, that's at most n squared, and we get n over 4. It's before. Hopefully I haven't made any mistakes. Tell me otherwise. And it keeps going. At the bottom, you get t of 1. Eventually, you hit the base case. Then the algorithm terminates, and it takes t of 1 time. And what this recursion tree is capturing is how long the algorithm takes, right? I split it into these subproblems. I have to add them up. And then this is where the real cost comes in. So if I add up all of these numbers, that'll be t of n. So that's my goal. The total of all of these nodes is t of n. Okay? So now there are many ways to add up a bunch of numbers. And one way, this is really obvious once you look at a tree, is you can add it up level by level. So let's do that. Here, it's n squared. That's easy. Here, I won't try to get it right. 5n squared over 16. Pretty good. That was quick. Okay, don't answer the next one, though. What's this one? Here, we need a really good arithmetician. That takes a while to work out. Oh, someone has the answer? This is 25. All right. Good. 256. Okay, what's the next term? This one's a little harder because it's all black. Don't multiply it out. Just write the closed form.
5 to the k, 16 to the k, n squared, 16 over 11 times.
Wow, that was a little too much. So you say, here it's 5 over 16 to the power k in general if you're at depth k. Okay. This is like this game, I give you a sequence of numbers. What's the next number? To figure out the sequence. And here we're really using our intelligence. This is not rigorous at all. And you said what the total sum is, but that's okay. Let's write it out first. So we have n squared. We have a 1 at the top, and then 5/16 at the next level, and then 5/16 squared at the next level, and it keeps going. For some depth, but you all see immediately, doesn't matter how far we go, this is a geometric series. And so it converges to a constant, even if this tree went down to infinity. It stops after logarithmically many levels, but could even go to infinity. This is at most order n squared. Okay, it's theta n squared. And you can work out the constant, but that's nice. So immediately we got that this recurrence had the solution order n squared. Now, we weren't exactly rigorous in doing this, so there are more details. You have to prove that at each level you get this cost, 5 over 16 to the k. So I write this down so you have in your notes. This is not a complete proof. One thing you could do is prove this. The other thing you can do is just use the substitution method. Now you have the right guess. You just plug in this guess into the substitution method. You apply induction, which is your friend. Induction tells you that everything works out. So that's usually the easiest way to proceed. Instead of using recursion trees explicitly, you just use them to generate a guess. Good. Lots of time. That's the end of recursion trees, unless there are any questions. Good. The next thing I want to talk about is how to find a good piece of chalk. Here. That was quick. Next thing I want to talk about is the master method. The master method has a really important name, so it better be important, right? Okay, this is the last thing we'll be talking about today. It's a very useful tool because it's sort of like magic. You give me a recurrence of a particular form, not just any one. The stuff we've been talking about so far works for any recurrence, pretty much. The master method only works for a special kind of recurrence of this form. Which is pretty general. It says if I have a recurrence where I take a problem of size n, I split it into a subproblems of size n over b, and then I solve those recursively, and then I merge them for a cost of f of n for some function f. So that applies to a lot of algorithms. It applies to merge sort. It applies to binary search, which you should all know. We'll see lots of examples of this. And most of the time, the master method will just tell you the answer. You have to memorize the master method, and it will take us 3 boardfuls to write it down, so that's a little bit of effort. But once you know it, it will be your friend, because it will solve these instantly, which is great. You don't even have to think. OK. There are some catches, but they're minor catches. So one thing we need is that A better be at least 1, I believe, just so that you're splitting it into at least one problem. Check, yeah. B, on the other hand, better be bigger than 1. Otherwise, this is infinite. So that wouldn't be, assuming f is positive. Right, you have to split the problem. And finally, f should be asymptotically positive. What does asymptotically positive mean? Never heard it before. Who's been reading the textbook? One person? More than one person? What should it mean? Forget whether you've read the textbook. That's cheating. Asymptotically positive? I don't know. Asymptotically n squared, we know what that means. Asymptotically positive? A couple guesses if we're kind of right. F is positive as it approaches infinity. Yeah, let's say like f of n is bigger than 0 for sufficiently large n. Once you get past sufficiently large, of course, means that once n is at least n naught for some n naught, then it becomes positive. So on the limit, it's positive. Right. This notation is somewhat intuitive, so we're in luck. OK. Now, what is the master theorem? The master theorem says, basically, given these assumptions, that it will tell you what t of n is in most cases. And there are 3 cases which cover pretty much everything. The cases come about by comparing 2 functions. We're going to compare our merge cost, f of n, with another function, n, to the log base b of a. That should not be intuitive yet. It will be intuitive later on. Okay, I would prefer to state the theorem before I say why this. But I will give you the intuition first. The intuition says f of n is our merge cost. N to the log base b of a is how much time we spend over here in the recursion. Okay, that's a rough idea. So there are 2 terms in the recurrence t of n. Sometimes this is the important term. Sometimes this is the important term. We've seen an example of that, I think, over here. What was important in this recurrence was the n squared. That's what dominated. This other stuff, which came from adding up all these numbers, what was important was the n squared, which is at the very root. That's the merge cost. So sometimes that's the important thing. And sometimes this other term, n to the log base b of a, is the important thing. And so there are three cases depending on which way it goes. So the first case is that f of n is smaller. Now we mean a special thing by smaller. It has to be what's called polynomially smaller. This is what polynomially smaller means. So in words, you say that f of n is polynomially smaller than this other function, n to the log base b of a. Okay, it just says if you take the ratio f of n divided by n to the log base b of a, there's at least an n to the epsilon term of gap between them. So it's saying f of n is quite a bit smaller. But as long as epsilon is positive, that's all you need. Okay, so this is continuing case 1. Then we say the solution. So the master method is, if you're in this case, it just tells you what the answer is. It says, well, if f of n is small, the dominant term is the n to the log base b of a. And so the total cost, t of n, is just n to the log base b of a. And you're done. You can just say, by the master method, if you're in this case. The next case is f of n. I'll write this down in words first. This is really in quotes. F of n and n to the log base b of a grow at roughly the same speed. This is what you think, but there's a formal version of this. The formal version says, if I look at f of n and compare it to my n to the log base b of a, they should be pretty close in the sense of up to a polylogarithmic factor. Oh, dear. I realize I've not been following the notation of the course. The notation that we usually use throughout, you don't have to change this, but I'll usually use LG to denote log base 2. Oh, sorry, that's log base b. Good. That's fine. Here's the first time I get to use log. You pronounce this lug for some reason, for the obvious reason. So finish this. This denotes log base 2 of n. And here I've raised it to a power of k. The power of k goes on the outside. Okay, it doesn't mean iterated k times or whatever. Good. Okay, so this is saying if you take the ratio of f of n and n to the log base b of a, you're pretty close. There's some polylog factor. Now, k here is a constant. K should be at least 0. Negative numbers won't work. So if this is divided by log n, it doesn't work. The master method doesn't apply. But if you have nothing here, or if you have log, or if you have log squared, those all work fine. And again, the master method just tells you the solution. Now, I erased my recursion tree, unfortunately. What this says intuitively is that everything's balanced. Everything matters. Both of these terms, a times t of n over b and f of n, matter. And so you get something, because they're both around the same. So you get something that's close to both of them, but not exactly either. So you get, the master method tells you the cost is n to the log base b of a times another polylog factor, but the polylog factor is different. It has an extra log. Okay? That's the solution. We'll see examples of all of these after I finish stating the theorem, which has one more case. So case 3 is that f of n is bigger. And f of n should be polynomially bigger. So I should say it grows polynomially bigger. Polynomially faster. Okay, just to be clear, because I got it wrong before, if you specify the base of the log, you use log. If you want 2, you use log. And now we're in case 3. Now, case 3 doesn't immediately tell you the answer. It's a little bit different. You need another assumption. So let me first write down this assumption formally. Okay, just like case 1. But now we need another assumption, which is called the regularity condition. The regularity condition says, basically, the easy way to figure it out is you look at this term, and instead of t, you plug in f. I'll say why this makes sense in a moment. That should be at most some constant times f of n. And the constant has to be strictly less than 1. So that's the regularity condition. And then the theorem tells you the answer. It says, well, f of n is bigger than n to the log base b of a. F of n dominates. So t of n is actually proportional to f of n. So that's like the last example we saw with the recursion trees. F of n dominated. The merge cost dominated. Okay, what is this saying? I should say a little bit about that. But I don't have any room, so let me go over here. What's the picture? Well, this is actually part of a recursion tree. Sorry. Yeah. At the top of the recursion tree, you have a merge cost of f of n. Below that, you have a subproblems, each of size n over b. So now you can see what this is saying. If you add up these bottom costs, they should be strictly smaller than the top cost. Okay? So that at least gives you moderately better idea. I will come back to this picture. So I will reuse this figure later on. You may have to copy it. Before I tell you more intuition about the master theorem, I want to do some examples. So let me do them over here. Good. First example is one we've seen before. At the very beginning, t of n is 4 times t of n over 2 plus n. Let's do some work just to be clear what we're saying. We want to write this in terms of the master method. So you look, it's even vertically aligned, which is great. A is 4. B, what we're dividing by in here is 2. And f of n is n. Okay, now we have all the right terminology. And we check, OK, a is at least 1. B is bigger than 1. Good. F of n is always positive. Good. What else do we need? Well, we need to know what case we're in. So we want to compare f of n to n to the log base b of a. And then we'll be pretty much done. That's the great part. So all you have to do is think, well, log base 2 of 4 is, it's too easy, 2. Okay, I'll try to ask more difficult questions. So we have n squared as our n to the log base b of a. Okay? So now, which case do we fall into? Okay, this is a little bit trickier question. 1, 2, or 3? Would you like door number 1, door number 2, or door number 3? 1. Right. Why is it in 1? Because f of n is smaller. F of n is linear. N to the log base b is quadratic. F of n is smaller by a polynomial amount. Just write it down explicitly once. F of n is n to the log base b of a minus epsilon. And here epsilon is 1. And epsilon has to be greater than 0, so we're doing good. Okay, so that means we're in case 1. And case 1 just tells us the answer. I think it's over on this board. It says the dominant thing is n to the log base b of a. So we get t of n is n to the log base b of a, which here is n squared. Wonderful. That was a lot less work than what we did in the beginning of class with the substitution method. The only catch is we didn't get the constant. That is the way of the master method. You could work through the proof of the master method and figure out the constants, but we will usually live without the constants, and you work them out if necessary. So that's cool. Let's do another example. I want to cover all the cases. So the next one will look pretty much the same. The next recurrence will look the same, except I will change f to be n squared. So now, what case are we in? Sorry? 2. Right. We're in case 2 because now the f is about the same. In fact, it is exactly the same as n to the log base b of a. So, case 2. Good. Here we don't have a log term. Where's our log term? Remember, k can be 0, so you don't have to have a log term. And in fact, in the book, there isn't a log term, and it's in an exercise. But this is a lot more useful. That was one of the many revisions that didn't get into second edition, unfortunately. But the important stuff is there. Good. Case 2 tells us the answer. It says that you get an extra log term. So t of n is this f of n, or n to the log base b of a, which is n squared here, times a log n. Good. Also very easy. Case 3, it's a little more work, but not much. So let me, I need another board. So now I'll use the same recurrence, but change f to be n cubed, so that now f is bigger than n to the log base b of a, and so we're in case 3. So I'll just say here epsilon equals 1, I guess, because it's n squared plus 1. And we're in case 3. Good. Now, in case 3, we have to check this extra condition, the regularity condition. And fortunately, in this case, it will hold. Most of the time, it will hold. Most of the time, f of n is polynomial, and this will work out. But you have to check it, because the theorem doesn't hold otherwise. So we have a. Now, a, we want to look at this, but with f plugged in. So we have 4 times f of n over 2. That should be at most c times f of n. Okay, and we know what f is. F is n cubed. So 4 times n over 2 cubed should be at most c times n over 2 cubed. Sorry, over times n cubed. And this is true when c is greater than 2, right? 1. Wait. Better not be 2. 2 would be no good, right? C has to be strictly less than 1. So this is a good check. Either it's not holding, or 1 over C better be at least 2. So C is, let's say C is a half. I don't want to have to figure out which way works. So C should be between a half and 1. That's the right way. But if C is a half, it works. So I'll put in if, for example, C is a half. And so regularity condition works out. We're set. And we get the solution, which I think I can fit in here. The solution in case 3 is that f of n dominates. And so t of n is theta f of n, which is just n cubed. OK, so a little bit more work to get the regularity condition to hold. But still, the master method is easy. And when the master method works, it's a great tool because it solves things instantly. Let me give you some of the intuition behind the master method and what's going on. I wanted to do one more example quickly. Just to keep you on your feet, tell me 4 times t of n over 2, same setup. Now f of n is n squared over log n. Which case are we in? One answer. Anyone else? In between, right. Yeah. Somewhere in between case 1 and case 2. Doesn't fit. So this is no good. Master method doesn't cover everything, unfortunately. So occasionally, you run into things, into recurrences, where the master method does not apply, sadly. But I will mention that there are more general methods. And I think I even have time. Yeah, it's cutting it close. I won't mention the more general methods here, but in particular, there's something called acrobacy. Which allows you to solve, for example, this recurrence. And that should be covered at least in some form. There are many forms of acrobacy. Did I misspell acra? Cheat. Yes, this should be acro with an A, with 2 A's. There are many forms of acrobacy. Some of them cover this. Some of them allow you, instead of having exactly splitting into problems of exactly the same size, of roughly the same size, or slightly differing sizes. But most of the time, the master method is enough. Or you can use the substitution method or whatever. Good. Finally, I want to talk about the intuition, which I've been promising you. So what's going on with the master method? The easiest way to see the basic idea is to look at the recursion tree. Which I conveniently have half of here. So you just keep expanding the recursion tree. It's A, and each time you branch A ways, and you divide the argument by B. I'm not going to draw the whole thing because it would take me theta n log n work, or theta n work, I don't know. It's too much time for me because I don't have n time. I only have 10 minutes. So let's see. You keep going. Eventually, you get down to t of 1 a whole bunch of times. I won't write them all down here. And, well, that's the general picture for this kind of recurrence. Now we just need to add up all the numbers like we did before. So we'll add it up line by line. See, I think there's more room over here. So the top line I will do because it's easy. The next line is right. This one we actually did before. It's a times f of n over b. Same as the regularity condition. Okay, that's where that was coming up. The next one, I'll save you some work. So we have a of these nodes. Each one is branching a ways. Each of these has lots of children, a of them. You add them up, that's a squared of them. So if a squared f of n over b squared. Sorry. F of n over b squared, pronounced somewhat differently. Okay. And you keep going. At each time you have a to the I, f of n over b to the I. But I won't write that. One essential thing is what happens at the bottom. The bottom will turn out to be an important level. Okay, so we're going to count how many leaves are there here. And let's make a little diversion. If you have a tree of height h, let's say initially you have a tree of height 1, and the branching factor is a. The number of leaves down here is a. Okay, what if I branch again, also each time a ways. So now my height is 2. Number of leaves is a squared. Okay, this is pretty boring. We get down to the ith level. Total number of leaves is a to the I. Right. Good. It's just easier to abstract what's going on here. I know you've all seen that before. Now we have that the number of leaves in this example, well, we have branching factor a, but now the height. What's the height? Sorry. Log base b of n. Good. Write that over here. The height, h, is log base b of n. Because at each level, we're taking the argument and dividing it by b. So how many times do you have to divide the argument by b until you get to 1? That's log base b of n. OK, so the number of leaves is a to the power of the height, which is log base b of n. Good. Does anyone see how to write that in terms of something that we know and love by the end of this lecture? Something we've seen before. Right. This is also known as n to the log base b of a, which you will all remember once you know the master theorem. Okay, you just take the n, you put it down the bottom. You take the a, you put it down in the top. It sounds easier said than done, but you think of your powers and log rules. That's the right thing. Aha! That's where the n to the log base b of a comes up. It's the number of leaves. The cost at this leaf level is the number of leaves, n to the power log base b of a, times t of 1. That's the total cost at the leaf level. So what were we comparing in the master method? I've erased the master method. Sorry. We were always comparing f of n with n to the log base b of a. Because f of n was the top level, n to the log base b of a, up to a constant, was the bottom level. And so it turns out, if one of these is bigger, it dominates. If f of n is polynomially bigger than the leaf level, it dominates. If n to the log base b of a is polynomially larger than f of n, most of the time it dominates. Okay? And case 2 is when all of these levels cost roughly the same. Let me just write down that intuition so that you have it in your notes. So the idea is that in case 1, use the wording I prepared here. So remember, case 1 was when n to the log base b of a dominated. Okay? And what's going on here is that the leaves are what matter. If you look at the weight of each level, the weight is just the sum of all the nodes at each level. Then the weight increases geometrically as you go down in levels from the root level to the leaves. If it's a geometric series, all that matters is the big term, which here is increasing towards the leaves. So the leaves are what matter. That's why it's n to the log base b of a. This is not a proof, but this is what goes on in the proof. If you want to prove the master method, which you can see in your book, it's not very hard, you show that this is the case, that the weight increases geometrically. And so what that means is that the leaves have together a constant fraction of all of the work to be done, of the total weight. Okay, so that's why you get this theta. Next case. Case 2 was when, and I will make my life a little bit easier, let's suppose that k is 0. K, remember, was the exponent in the log term. So let's just forget about the log term. Then we have that t of n is theta n to the log base b of a times log n. Good. And here what's going on is the weight is pretty much balanced among the levels. Right? If you look at this recursion tree, at the top we have f of n. But now we know the assumption is that f of n is n to the log base b of a, if k equals 0. So that means this cost is within a theta term of this cost. And you can check all of the levels are balanced. And all the weight at each level is n to the log base b of a, roughly. Should put a theta. How many levels are there? We already computed the height of the tree. It was log base b of n, right? We can even be sloppy here. That's around log n within a constant factor as long as b is constant. So that's where it comes from. We have n to the log base b of a at each level. Of log n levels, the total cost is the product. Pretty easy. The last one, I'll leave it up, is case 3. And with case 3, we ended up with that t of n was theta f of n. And what's going on here is that it's the root that matters. The root is dominating. And in fact, if you look at the weight at each level, the weight decreases geometrically as you go from the top to the bottom of the tree. And so, let's see. What matters is the root in the sense that the root has a constant fraction of the total weight. Okay, so the total cost t of n is just theta of f of n. And that is the master theorem. And it's even a little bit early. So do you want to see the proof of the master theorem? Oh, that would just be so exciting. Nah. Let's all go home 5 minutes early. That is the end. Don't forget, problem set 1 is due next Wednesday, not this Wednesday. Come up here if you haven't registered yet.